Okay, now we're recording. Okay, so all of the assignments for the first module have now been posted, so it's up to homework 4 and also the quiz for module 1. And I tried to space the due dates out as much as I can. So
When was the first quiz?
that is due on February 27th. So we
You're saying it was already.
so the next thing coming up is, well, due tonight is homework 2. Homework 3 is due Monday. Although I think if I can,
Are you gonna skip that one?
what? Actually, what? Okay. Actually, if I can, if it'll let me, I actually want to push that back a bit.
Yeah.
Let's see if it'll let me.
Yeah.
Because then the next homework number 4 is not due until the 22nd. Quite a,
This
I think-
quiz on the 27th is online, right?
yes,
Okay.
yes, so it's somewhat different settings than a homework, but it's in the same site.
I think that homework should at least be due a week after the previous one.
That will not always be possible. I will come as close to that as I can, but yeah,
A week after we finish the topic.
that will always be true, or at least a week.
Try on the quiz or?
Let me check the settings.
I remember you told us about it. Can't remember it now.
I can't remember either. I just set it up yesterday. Okay. So what will happen is, the number of times that the quiz as a whole can be taken, 3 attempts. But also has it set for number of tries on each version of a question is 2. Okay. Yeah. So only a little more stringent than what happens on the homework. There's no time limit. Okay.
There's no time limit.
Right.
Yeah.
So,
I thought there was.
I thought about it, but I decided not to. Okay.
It's all random, so you may get like really annoying numbers.
Oh, that's right. I was wanting to adjust homework 3.
All you had to do with the graph is just like look.
I finished the homework 2 last night. One of my answers was literally like 70,000 over. This is the last couple questions.
Okay, homework 3 is due on the 15th. So for the time being, there's good spacing. Now, if toward the end of the semester, there's going to be, let's see. The number of assignments where I only spend 1 day in class covering like the topic, but so if there's a risk of having assignments bunch up, I might combine them or make them shorter. So I'll try to not have too high density of homework problems per day. So, in fact, the assignments that I had inherited from Dr. Chapman, I'd already combined some of them anyway. And therefore toss some questions. Okay. All right, any other questions concerning assignments and such and due dates and all that? Let's see, sometime before, we'll see, the midterm is on March 8th. So that's the last class we have before spring break. So sometime in late, like the last week of February is when I'll post the practice midterm and solution, so that when we have the review of a class before, we can talk about that. You'll have time to work through that. Okay. All right. Last time we saw a few ways to test whether a given series converges. I'm gonna see some more convergence tests today. And then we'll be done with regular series after today. Then starting next week, we get into power series. That's probably gonna be the worst part of a semester. Just to warn you up front, but the point is, once we get through that, then things will get better, so. Okay. Now. Here in class, I'm going to state all of these tests, under what circumstances can they be used, how to use them. I'll give examples for each one. There's additional information and notes about basically, in some cases, proving that these tests work. I was concerned that if I got into that right here, which is not in the homework, that would not be time well spent. Versus alternating. Series test. So. What is an alternating series?
Is it the one that flips between positive and negative sign?
It is, yeah. So the series of this form. Now, if you want particular going to be different, I'm just going to write it starting at n going from like 0 to infinity, or n going from something to infinity. And we have -1 to the n times some number bn, where these have to all be the same sign, either all positive or all negative. And then by multiplying by -1 to the n, that causes the terms of a series to be alternating in signs. That's where the name alternating series comes from. Okay. All right. An example of an alternating series. Now, actually, this particular series, you already know this as what kind of series? It is a geometric series, but we can also, it is also an alternating series. If I take the -1 to the n and write it separately, I have 1/2 to the n. So this is the bn part. All of these are positive, and then we multiply by -1 to the n to cause the sign flipping effect. Okay. Now, so it turns out it can be somewhat easier to check whether an alternating series converges as opposed to other series, because I mentioned before that in order for a series to converge, it's necessary, not sufficient, necessary that the terms at least go to 0. And for generally speaking, them going to 0 is not enough to ensure convergence. But in this case, it actually is. So so we consider, I'm just going to write a generic alternating series for purpose of stating the alternating series test. And we're going to assume here that the bn's are all positive. So if you have a series that fits this form, like this one right here, does. Okay. So this would start out with b0 minus b1 plus b2 minus b3, and so on. Now.
Oh wait, Professor?
Yes.
Was that a DN up there next to under alternating series of form? Is that a DN? Or is
That's a B.
Okay. I was thinking that was a D. Thank you.
Okay. Oh, is there some? Okay. All right. Make sure. Okay. All right. So if these conditions are satisfied, first we must have these numbers steadily, at least not increasing. So they don't have to be strictly decreasing, and that would require a strictly less than, but as long as they're not increasing. And this has to be true for all indices n. And these numbers Bn have to go to 0. If these conditions are satisfied, then a series converges. That is the alternating series test. Questions so far about that? That's the state of. I'll do an example in a second. So as an example, we have any plus 1 to the n. Yeah. Okay. Now, we'll see if this series converges. Now, Bn in this case is n over n squared plus 1. Now we want to be sure that this is decreasing or at least not increasing. And that it's going to 0. Is it going to 0?
Yes.
Yeah, so this certainly goes to 0 as n goes to infinity. In this case, the decreasing part is, and you can tell that it is getting smaller and smaller, just because the denominator is growing faster. Now, as a way to be really sure that this is decreasing, you can rely on something you learned about in Cal 1. Well, you get a function. Let me find a function f of x, which will be this function, running x in place of n. Okay. How can you tell if a function of x is increasing or decreasing?
Looking like the hospital do that.
That's about the limit, though. Derivative. So at any particular point, you can tell a function is increasing or decreasing by examining its derivative. So derivative, in this case, what would I have to use for this? Yeah, quotient rule, yeah. Okay, so then we have up top, we have 1 minus x squared. So I have x squared here and minus 2x squared here. All over squared plus 1 squared. Now, we only care about how this function behaves for n going from 1, 2, 3 up to infinity. So we really only care what's happening here for x greater or equal to 1. So what happens is this derivative is going to be less than or equal to 0 for x greater or equal to 1. So it is non-increasing. So because of this derivative, at least the way we care about is never positive. These numbers, n over n squared plus 1, really are decreasing or at least non-increasing. So by that, we can conclude that the series converges. Now, you don't necessarily have to go to all this trouble to see if the expression you're given is decreasing. In some cases, it would be simpler to determine. For example, if you had, like, for instance, if I just had 1 over n, or if I had 1 over 2 to the n, it's more obvious in that case. But I want to show a case where it's not as, you can't really tell just by looking. There is something that you can do to be sure. And also to show you that when you're learning Cal 1 and Cal 2, just because you're done with those classes, sometimes you still need those things. Okay. Any questions about this one? Okay. Here's another, like a simple one to work with. Now, I've told you before, but series 1 over n, that's a harmonic series that diverges. But what if I multiply it by -1 to the n? What's going to happen with this series?
Right.
It is an alternating series. Does it pass the assumptions of the alternating series test?
Yes,
Yeah, it does. Yeah, because this expression 1 over n is definitely decreasing as n goes to infinity. It's also going to 0. So this series converges. Is because of that alternation, that -1 to the n is what made it converge. And but now, if I recall the previous example, but I take out the sign flipping part, I just have n over n squared plus 1. How does this series behave? Does it converge or diverge? So one of the tests that was covered last time can tell you. Limit comparison test is helpful here.
Wait,
Limit
Professor.
comparison with what simpler series?
1 over,
1 over n. And why did you choose 1 over n? What led you to that choice?
because take the leading coefficients.
Yes, so the top is degree 1, the bottom is degree 2. You take the difference. So you do limit comparison.
Professor, what's the word that you have to the left?
Whereas,
Okay.
if you perform a limit comparison test to this series, just plain old 1 over n, what conclusion does that lead you to? It diverges. Yes.
Harmonic series doesn't converge.
Right. So because the limit of this over this is going to be 1, the limit comparison test applies. They both have the same behavior. This one is known to diverge, therefore this one diverges too. So here we have an example of a series where if you let the signs flip, it does converge. Take sign flipping out, it doesn't. And this brings me to, there are actually 2 forms of convergence. So, oh, we have a lot of people online. I think the first day we had like 3 or 4, now there's like 9. So wait till the end of the semester when there'll be nobody here but me.
I took it all over again.
I might get in trouble for that, actually.
This is a really small room.
Yeah. Yeah, when I saw originally that there's 32 people in the class, like, how are we gonna fit in here? But. Okay, so. So a given series, AN, is said to converge absolutely. So converge absolutely if the series that you get by taking the absolute value of all the terms converges. So for instance, well, actually, none of the examples currently in the board do that. But if I had like -1 to the n, 1 over n squared, that would converge absolutely because we take the absolute value and you get 1 over n squared. That's a P series that converges. The other kind is called conditional convergence. So a given series converges conditionally if the series by itself, as written, converges. But if you take the absolute value of all the terms, if that series diverges, then it's conditional. So it's like a weaker form of convergence. It may not converge to its sum as rapidly. So this series right here converges conditionally. Because it turns out the sign flipping is necessary to bring about convergence. If you take the absolute value of those terms, you get the harmonic series, and that divergence.
There ever a situation where you have the terminology to have?
Yeah, it seems like a lot of rules to.
Well, it does lead to some homework problems, but okay. And I'm trying to think of where the distinction like is important for something else, like outside of this class. And no, I haven't seen it. Where these kind of series come up is, for instance, when we will see power series later, power series, the terms are a function of x. And you're going to find that it will only converge for a certain x in some interval, and then they'll converge absolutely. But what about the endpoints of an interval? Do they converge or not? And you'll find in some cases, even if they converge absolutely inside, the convergence at the endpoints is either conditional or maybe it doesn't happen at all. So, but as far as like the application of conditional convergence, you'll have to have someone else. And they'll probably be like, okay. Any questions about what we have here with these alternating series? And there's actually one more thing we can do with alternating series. If we know it converges, we can actually easily get an idea of an estimate of the sum. So far, we only know how to get the sum for a geometric series or telescoping series. For alternating series, we can't get the exact sum easily, unless it's some other category like geometric. But we can get a ballpark value. Okay. So, this is called the alternating series estimation theorem. So if this series, same generic alternating series, has to satisfy the assumptions of the alternating series test. Therefore, we'll know it converges. And this is another way of writing that the BNs go to 0, the BNs are not increasing. So those same conditions have to apply. Okay. Then I'm going to define the notation here. So we know it converges. So I'm going to let S equal the sum of the series. And then I will define Sn be a partial sum. Actually, okay. I can check my notation here. I have to use a different letter in here because I'm summing up to n. So this is a partial sum. We can conclude the following, that the difference between the exact sum and the partial sum less or equal to the magnitude, the absolute value of the next term in the series. So if you start, B0 minus B1 plus B2 minus B3 and so forth, up to say B8, then how far away you are from the true sum is at most B9. And depending on the series that you have, you might be able to use that to figure out, suppose you want the sum estimated to a certain error, like suppose you want to estimate the sum of the alternating series to say 3 decimal places. You can figure out how much of a partial sum you need to get that close. By making this remainder small enough. So an example of that. So this series that, well, admittedly it's a geometric series, but there's also an alternating series. Okay. So we want a partial sum so if I use S to refer to the exact sum, we know this series is convergent. We want the difference between the true sum and the partial sum to be at most 1/1000. So we want to figure out what does n need to be to make that happen. Well, what we know that this difference is less than or equal to the absolute value of the next term. that'd be 3 to the n plus 1. So we're going to solve this inequality for n. And that will tell us how many terms we need to include in a partial sum to get that close to the true sum. So this is how you apply the alternating series estimation. Yeah. Questions on how got to this point? So all you're doing is you're looking at the next term. How?
Professor?
Yes.
Okay, how do you have 1/3 n plus 1, and also what's the word that starts with an S after that?
I'm sorry, what are you asking?
How do you have the 3 to the power of n plus 1?
Okay, so whatever expression we have here,
Mhm.
we need to replace n by n plus 1. So that's what this estimation theorem is saying over here.
Oh, okay.
Yeah, so all I'm doing is applying this.
Okay. Then, okay, what's the word that starts with an S after that?
Sorry, before.
What's the word that starts with an S after that?
Oh. This. Yeah, solve this inequality for n.
Okay.
Sorry, I know my penmanship's not the best. Maybe it's literally the worst. It goes like this. If I'm writing this on paper, it's a whole lot worse than this. Even I can't read it anymore.
Those notes you have, are they available online?
Yeah.
Oh, yeah. Never,
Okay.
very Canvas.
I didn't see it, sorry.
Okay, yeah, the main page of Canvas, you'll find it there.
So do you think?
I do keep updating them
It's on the syllabus.
as I go. So, if I want to solve this for n, how would I do that? Well, what algebraic maneuver would I need to isolate n?
Yeah.
Yeah, you'll need the natural log. So, okay, so I can write this as 3 to the minus n plus 1 is less than or equal to 10 to the minus 3. So then if I take the natural log of both sides, I have minus n plus 1 natural log of 3 must be less than or equal to minus 3 natural log of 10. So then I can use this inequality and I'll carry out the rest of the algebra to isolate n. Now, well, for one thing, I have minus on both sides. So the inequality will flip. I can divide both sides by natural log of 3. And then I have this plus 1, I can move to the other side. So what I get is n must be greater than or equal to roughly 5.29. So as long as
What do you do with the -3?
oh, I forgot about that.
Yeah.
Where'd it go? Oh,
Something in front of the 10,
Uh,
the natural log of 10.
yeah.
Sorry, I just,
Oh, no, I totally dropped it. It was right here in my notes and I didn't write it. So as long as so if I look at Sn, as S6 rather, So that's the partial sum that I need. Because, well, actually, yes. So I need to round this up to the next integer to be sure. So S6 would be 1 minus 1/3 plus 1/9 minus 1/27 plus 1 2/43 minus 1 over 7/29, 0, 1, 2, 3, 4, 5. I need one more. That's going to be plus 1 over 2,187. I'm not going to do that fraction in my head. But I mean, adding, subtracting all of these up, but this partial sum presumably will be within 0.001 of the true sum. Okay. Using geometric series, what is the exact sum?
Professor?
But
Okay, at the very bottom, when it says 3 ln 10 over ln of 3,
yes,
what does that go? What does that go to after that? It's cut off.
well, there's an implication. Oh, whoops, hold on.
N is greater than.
It's just barely cut off.
Oh, that's strange. Yeah, my apparently what it shows on my screen is not reliable. Is that better?
Well, okay, yeah. We only saw the 5 earlier. Is that 27 afterwards?
0.29. 5.29.
Okay, we only saw the 5.
Yeah.
Okay, although although the left side's a little is the left side's not showing as well. Could you move just slightly over to the left?
Okay, like that.
No, sorry. Oh no, sorry. The other way. Yeah.
Right, back it up.
That's good. Oh,
Is that
No.
better?
back. Okay, yeah, there we go. Thank you.
Yeah, but apparently what I see in my little window is not the same as, oh, you know what? I forgot to set spotlight for everyone. Oh, boy. I hope it doesn't mess with the video that I record. Well, no one else has their camera on, so hopefully it'll be fine, but, okay. Yes, because right now, like on my little corner of the screen that shows what my webcam is allegedly capturing, I totally shows the whole board, but apparently the viewers at home can't see all of that.
It's usually cut off in the border.
Dang it. Okay.
So what is S6 supposed to equal? Like,
Okay, so that partial sum should be within this much of the true sum.
What is the true sum?
Well, the true sum, we'd use the formula. So S is equal to A over 1 minus R. For this case, A is equal to 1. R is equal to minus 1/3. So you get 3/4 is the true sum. Now, okay, I'm gonna change.
So the true sum is the sequence.
That's the sum of the original series. Yeah. This should be close to 3/4. Let's find out.
it's 0.7439.
Oh, you did already?
Yeah, so
So,
it's,
that feels not close enough. Wait, 0.7439.
mhm.
I try again.
Oh, yeah, what happened? Okay. Yeah, because that's S0 and 1, 2, 3, 4, 5, 6. Okay. That's a little puzzling. That's 27. Oh, I know what I did wrong. My power's 3. I missed the power
Yeah,
of
I
3.
was
Which one did I skip?
81.
Yeah, I leapfrogged from 3 cubed to 3 to the 5th. So then if you take your total, subtract out the 1/21/87 and add in 1/81. Well, actually, no, it's all thrown off because never mind, don't do that. So, okay. So. Plus. Minus 1
This is A1.
plus 1 divided by 1 minus 1 divided by 243 plus by 7.9 is 0.7503. Okay, so this is,
So
So that was-
okay. So that worked, okay. Yes, once you wrote down the right numbers, the estimation fair worked like a charm, go figure. Okay. Okay, I've been using up all my time, thank goodness. All right, any questions about this one?
Will it ever say like if it's 3,000, 1,000 above or below the actual sum?
Wait,
Like, can you ever figure out if it's gonna be like above or below?
actually, yes, you can, because, depending upon whether it's computing a odd or even partial sum, because what happens is, in this case, where your BNs are positive, what happens is the, I have it written down, and I'll make sure I get it right. Okay. The even partial sums are always above the true sum, and the odd partial sums are always below it.
Okay.
So, like, yes, so this is S6,
Makes sense.
S5 would be below, it keeps bouncing back and forth. So yeah, so not only do you have an idea of the magnitude of your error, you definitely know the sign of your error. So I could, if I were to go ahead and compute S7, then I'd be bracketing the exact value. Question? Now, there are a couple more convergence tests. Actually, yeah, one more example concerning absolute convergence. Just as an example, if I have this series, cosine n pi x. What? Oh, okay. Over n squared plus 1. Now, this is a series that actually depends on a parameter. So we're summing, so in other words, your in terms of series, your an depend on x. Now, but what you can do to determine whether the series converges, regardless of what x is we look at the absolute value. So if you're not sure what to do in the series, like, because depending on the value of x, these values can be both positive and negative. But if I go ahead and take the absolute value, at least everything here is positive. Now, what do I know about cosine and how big it can get? Yeah, between -1 and 1. So this is less than or equal to 1 over n squared plus 1. So I can compare to this series over n squared plus 1. Now, does this series converge or diverge? 1 over n squared plus 1. It converges.
Convergence on zero.
It converges what?
Does it converge on zero?
What do you mean by on 0?
Or like, or never mind,
Okay,
forget what I said.
okay, but it does converge. What test is good to determine that this converges? Limit comparison with what series? Yeah, it's the simpler series, 1 over n squared. All right, so by doing limit comparison with this series and this one, this converges, therefore this converges. By regular comparison test between this series and this one, because this series converges and this one has terms that are smaller, this converges. So this series converges. Also, because we examined not the original series, but the absolute value, we know something more than that. It converges absolutely. I'm sure you'll see better knowing that. That's not just convergent, it's absolute. I had a sarcasm sign as showing. So it converges absolutely by comparison to the sum of 1 over n squared plus 1. So if you have a series that has positive and negative terms, try just focusing on the absolute value, and that might be easier to work with than the original. I said x equal to 1 here. Cosine n pi is actually equal to -1 to the n. So that will be the alternating series. But here, if x is something else, who knows what these values could be? But we know we're between -1 and 1. That helps us determine that it converges. Questions about that one? Two more tests state. This one actually one that'll be quite useful later on. It's called the ratio test. Okay. So suppose the series you're given is this sum of terms an. What we can do is take the limit as n goes to infinity of the absolute value of an plus 1 over an. So you're taking two consecutive terms over two consecutive indices, looking at their ratio. And if it exists, if there is a limit at all, this could tell you something about how the series behaves. Now, if there are three cases, okay. I know it's all out of order. Okay. So first case, L is less than 1, strictly less than 1. If that happens, series converges absolutely. So that's the result we'd like to get. Second case, L is greater than 1. Then the series diverges.
Professor?
Yes.
Hey, what's the word before the first sigma an? What under ratio
Given.
test?
Given.
Oh, given. Okay.
Finally, the only possibility left, of course, is L equal to 1. In that case, unfortunately, this case we don't want. We have no idea. The test is inconclusive. We'd have to try a different test. And it's going to come a lot actually with power series, where for certain x, it's common to try a ratio test, and for certain x, you'll get this result or this result, but then for x at the end points of some interval, you get 1, and you have to try something different. Okay. Showing an example of that. I don't really like the example I have in my notes, so I'm just gonna make up a different one. Okay. Now, if I write a series like this, you would identify it as a geometric series, but I'm gonna change it a little bit. I'm gonna throw a factor of n squared in the denominator, so that makes it a little less clear what to do based on tests that you've seen before. So if we try the ratio test, then we'll let L be equal to the limit as n goes to infinity of. Okay, so up top, I'm gonna put this expression with n replaced throughout by n plus one. So that would be 2 to the n plus one over 3 to the n plus one. And then we have n plus one quantity squared. So this is an plus one. Down below, we put an. Now, as fractions go, this is kind of a mess. And what I like to do in these cases, I just take the fraction down below and flip it and multiply. So you end up with, okay, 2 to the n plus one over n plus one squared, 3 to the n plus one, and then I have n squared, 3 to the n up top, and then 2 to the n down below. So you end up with a situation like this where a lot of things can simplify. For example, here I have 2 to the n plus one. Down here I have 2 to the n. Oh, sorry. Sorry, what?
Where did that eight to the n plus one come from?
Oh, I was late. This. Yeah. Okay. So now if I group similar expressions together, for example, powers of 2, powers of 3, this square, I have 2 to the n plus 1 over 2 to the n. Then I have 3 to the n over 3 to the n plus 1. Then I have n squared over n plus 1 squared. So now we can try simplifying this as much as possible. So this simplifies to 2. This, subtracting the exponents, simplifies to 1/3. And then what happens to that whole, the whole fraction, n squared over n plus 1 squared? What happens to that as n goes to infinity? It approaches 1. So the limit turns out to be 2/3. In other words, this n squared there did not contribute anything to the limit. So that's actually a shortcut for the ratio test. If you have just powers of n or polynomials of n in your expression, or whether it converges or not is going to be determined by other parts of your expression, like the geometric part. So this is less than 1. Therefore converges absolutely. The question on how that one played out. If I had flipped it to 2 and a 3, this would have diverged. And the thing is, I still have this n squared denominator that's getting larger and larger, making the whole fraction smaller. but it's not, it would not be enough. If I had 3 to the n up top and 2 to the n down below, I'd have 3 halves to the n. That would be growing so much faster than the n squared.
The n squared, you said that play any role, is that always gonna be the case or there are exceptions?
Anytime,
It's overpowered.
because what happens is, if you have any polynomial either part of a fraction, doesn't matter whether it's above or below, you're gonna have that polynomial in here evaluated at n, and also at n plus 1. Limits that's always gonna be 1. So yes, you can just ignore it. Other things like geometric, exponential functions, factorials, things like that will be decisive when it comes to convergence. Other question? One more convergence test, very last one. Kind of similar to the root ratio test, it's called the root test. So you just take a different limit. So instead of the ratio, you look at the absolute value of an, and you raise it to the 1 over n power. So you're taking the nth root of absolute value of an, and you take the limit of that as n goes to infinity, and see what you get if there is a limit at all. And the rest of this that I've written here for ratio test still applies. It's exactly the same. So if the limit is less than 1, converges absolutely, greater than 1 diverges, less than 1 inconclusive. The usefulness of this test is kind of limited because if you take your whatever expression you're summing, you take the raise it to the 1 over n power, or you're taking the nth root of it, that might not be a very easy expression to work with. It's best used if what you're summing is already being raised to the nth power. Because then you raise that to the 1 over n power and just cancels out. Otherwise, I wouldn't bother.
Hi, Professor.
Yeah.
Oh. Actually, I was gonna say really quickly, I was confusing how. Sorry, I forgot I was unmuted. How do you get 2 times 1/3 at the end there?
Because before I had 3 to the n over 3 to the n plus 1 is what was written, what I just erased.
Mm.
And if you subtract the exponents, so this
Okay.
simplifies to 1/3.
Okay, so it hadn't gotten, so it's simplified. Okay. Okay, I'm with you now. Okay.
Okay, if I erase the rest of that.
Hold on a second. Okay, got it.
What?
Got it.
Okay. So now here's an example where the root test is helpful. Zero to infinity. Okay. 1 over pi times inverse tangents of n, all that raised to the nth power. So what you do is you apply the root test. Someone who's been doing research applied math for decades, I can assure you that nothing like this will ever pop up in the wild. Well, actually, I think it's about a
Well,
lot of problems.
if it doesn't pop in the wild, is it fair to say it won't pop on a test?
Well, this might. I gotta give something about the root test. So,
Is the absolute value that's in the, is that still there, or is it just the A?
but yeah, we do take the absolute value of an first,
Okay.
and then raise it to 1 over n power. But yeah, like, calculus textbooks are full of problems that are like basically contrived to,
But that never happened.
yeah, because they're meant to test certain skills. Now, it's possible some of those skills, depending on what area one
You're
works in.
absolutely useless.
Yeah.
Can't really test it, but it never happened before, right?
So, I mean, several of you have taken or are taking or will take, Math 326, linear algebra, where you're solving like a system of maybe up to 4 equations, 4 unknowns, doing your row operations and so forth. And, that was actually, that was what people did, for a job back in the 1940s. People would literally sit at desks all day and they'd be solving systems of linear equations on paper because electronic computers had not been invented yet. And their job title was a computer. What do you do for a living? I'm a computer. And then electronic computers came along and those jobs went away.
Professor,
Yes.
it was number 3 a ratio test?
Yes.
Yes.
Oh,
My numbering system might have been a little messed up. I spent so much time on alternating series tests.
I don't know why, but like a lot of the stuff I have wait, hold on, did you just erase ratio test and put root test where it was?
Yeah.
Okay, because I'm like,
Much of this changed.
okay, okay, okay. Also, if it says if limit goes to n as n goes to infinity, absolute value of a n, was that a n plus 1 over a n earlier, or?
For ratio test, it was.
Okay, for the root test, it's pretty much the same thing, except that that's just changed.
Yeah, because what I wrote for root test versus ratio, not much had to change. The only thing that changed was root instead of ratio and this.
Okay, I'm getting confused because I thought I was seeing the different changes and I'm like, and I didn't. Okay.
Okay. But yeah, like a lot of what happens in linear algebra is definitely not realistic. And I can give a real story in my graduate class on the subject. Okay. Now we have, to apply the root test, I'll take the absolute value of this and raise it to the 1 over n. So the original expression is being raised to the nth power. And then I raise that to the 1 over n power, so the exponents conveniently cancel. Wow. And we get absolute value of 1 over pi, inverse tangent of n. So now we need to take the limit of this as n goes to infinity and see what we get. So the limit as n goes to infinity of 1 over pi, inverse tangents of n. Can anyone tell me what is this came up once before? What is the limit of arctangent as n goes to infinity? Pi over 2. And then we divide by pi. So we get 1/2. So the verdict is this series converges absolutely. All right. And that's the last series convergence test. What?
How does it equal 1/2?
Oh, this converges to pi over 2. And then we divide by pi. So that 1 over pi factor in here was necessary. If it had not been there, L would have turned out to be, the limit would turn out to be pi over 2, but that would spell divergence. Pi over 2 is roughly 1.57. Okay. I think you'd want to ask some homework questions or maybe other people too.
I'll pull it up on my phone.
Okay. Okay. Okay, the telescope. Okay. And you can, this from homework too. What's the series? Can you read it off, please?
I forget what it is. Ln, 2, and then parentheses k plus 1, parentheses minus ln 2k. I don't have that exactly.
K goes from what?
K equals 3.
From 3 to infinity?
Yeah.
Okay. So what happens in this case, you look at partial sums. I'm going to invoke my own calculus professor from way back in the late 80s and say, would it be possible, we were his exact words, would it be possible to stop all the gibberish? It's very distracting. Okay, so what we get, we do partial sums, we get ln 8 minus ln 6 plus ln 10 minus ln 8, so forth. And we see, for instance, the ln 8s will cancel out. And if you were to keep going, like the next term is ln 10 would cancel out. But if you think what that means for a partial sum, so partial sums, well, if you just take just one term, you have ln 8 minus ln 6. The next time, if by throwing in the second term as I did here, the next one will be ln 10 minus ln 6, and then ln 12 minus ln 6. But then what's happening to these partial sums? As this is for k equal 3, k equal 4, k equal 5. Now, this minus ln 6 is always going to be there. But then you have to think about what's happening to this part as k goes to infinity. You can see the trend. And unless that this sequence of partial sums is converging to some value, you have to conclude a series diverges. And oh yeah, there was an example in class that was kind of like this.
Yeah.
And actually, we did that example with this homework problem in mind. There's still a little time. Are there any other homework questions?
Professor?
Yeah.
On the second line, is that equals ln of 8 minus ln of 6?
This is, yeah.
No, oh no, above that. Above that.
Oh, above this?
Yeah, is that
Right,
ln of 8 minus ln of 6? Is that what it is?
That's what this says, yes.
No, above that, the one above that.
Yeah, ln 8 minus ln 6 plus ln 10 minus ln 8. And then the ln 8s cancel.
Minus. Okay.
Also an ln. Any other questions about anything? Just want to make clear, late passes can be used either for these homework assignments or for quizzes. If you use a late pass, it's all about setting how many late passes could one use. You only ever, if you use one at all, you only ever need to use one, because one late pass gives you till the end of the semester to finish it.
Okay, what do the partial sums say? Those partial sums, what's the list of those?
Okay, ln 8 minus ln 6, ln 10 minus ln 6, ln 12 minus ln 6.
ln 10 minus ln what?
6.
And ln 12 minus ln 6?
Yes, these are all ln 6.
I got it.
All right. Yeah.
See you next week.